In the name of God, the most compassionate, the most merciful. Greetings to my dear friends. Today, I want to talk about digital joint mapping using the Cloud Compare software. I will briefly present the main points regarding the measurement of structural features on rock mass outcrops. Generally, we usually measure 3 types of features on rock outcrops. The first is the exposed plane, which are the discontinuity surfaces visible on the outcrop, and we can observe these discontinuity planes. The second feature is the trace, which are essentially the lines of fracture traces on the outcrop, shown in blue in the interface. The third feature is the edge, which is shown here in red on the interface. These are also lines of discontinuity or joint traces on the outcrop. Usually, we can easily measure these 3 features in the field using common tools like a tape measure and compass. However, when we want to estimate these digitally, we need 3D models. If we have a 3D model of the outcrop, we can digitally perform joint mapping using Cloud Compare software. In fact, we can easily do joint mapping with Cloud Compare and the Compass plugin. For example, I will import a very simple 3D model of a rock mass outcrop into the software and start working with it together. The model I am importing here is a mesh 3D model, meaning it is not a point cloud, and it is also textured, meaning the surfaces have a texture. The first point I want to mention is that the Compass tool, which you can access from the Plugins tab in Cloud Compare, only works with point clouds. So, if you want to use this tool on mesh models, it will return a not valid entry error. Therefore, it is better to first generate a point cloud and then use this tool. To generate a point cloud, select the 3D model here and apply that a sample points function. By default, it samples 1 million points, which is sufficient for my model. If you create a point cloud with more points, it might cause processing issues, and if your model is very large, the software might crash, as it is not very stable in this regard. We have now created our point cloud. Next, check its resolution. Here, I will hide the mesh model so you can only see the point cloud. The resolution is sufficient for you to identify the traces. I will show both models at the same time because you need the visual capabilities of the meshed model to better identify the traces and correctly select the discontinuity planes, edges, and traces. Therefore, both the meshed 3D model and the point cloud are set to visible, and we select the point cloud. Then, go to the Plugins tab and select the Compass plugin. There are various tools here, and I will briefly introduce them and then go directly to the plane picking and trace picking tools, as these are the 2 tools needed for digital manual joint mapping. By default, this plugin has 2 modes: Compass mode, which is suitable for measuring geological structures, and Map mode, which is more for geological mapping and provides more tools. However, I select the Compass mode. The first option here is the picking tool. If you have already made some picks and want to select them, you use this option to select previously made picks. The next tool is the exposed plane tool, which allows you to pick the exposed planes on the outcrop. The next tool is the trace tool, which lets you pick traces, and the last tool is the lineation tool, which we do not need. So, we only need the plane tool and trace tool here, and I will explain these in more detail. There are also some settings, which I will briefly explain later. First, let's go to the exposed planes, where you can observe the discontinuity plane. One point to mention here is that if your 3D model is being used in Cloud Compare for joint mapping, when you zoom in, some parts of the model may disappear. To fix this, go to Camera Settings and uncheck the Near Clipping option. If this is checked and you enter a value here, when you zoom in, parts of your model will disappear. So, if by default this is checked in Cloud Compare, you may need to uncheck Near Clipping so you can zoom in and, depending on your texture resolution, see the details. In this section, we have a discontinuity plane. you can easily fit a plane using the plane tool. Here, you see a red circle, and I can now click and select a plane here. However, I want to make this circle larger because the outcrop I see here is large, so it should match the size of the plane I want to select. So, I click once, and the software asks if I want to create an octree to make it easier to select surrounding points. The software automatically creates an octree for your 3D model or point cloud, and I select the fast option so the processing is quicker. When the octree is created, it will be much faster to find and select the points around where you clicked. I go and use the precise picking tool, and this is the specific plane that you have essentially selected. Based on the neighboring points you meticulously chose, it carefully calculates an average value and then precisely fits a geometric plane to that particular area. The prominent green vector you clearly see is the normal vector of that fitted plane, indicating its orientation in space. To increase accuracy, we fit another plane in this area. Basically, we try to cover as much of the rock face as possible so that our measurements are more precise. Now, if you want to rotate this model, it's really easy. When you're inside the plane tool, you can just click and rotate it to see how it looks. When you do this, the tool actually comes up and fits a new plane and axis based on where you clicked, just like that. If you simply left-click and then carefully drag your mouse to precisely rotate the three-dimensional model, this incredibly useful and highly effective tool works absolutely perfectly and effortlessly lets you smoothly rotate your entire model and meticulously view various different planes, such as this one, and accurately fit planes to them as well, with great ease and precision. I can easily rotate my model. To pan your model, you can right-click with the mouse and move the model around like this. For zooming, you can use the mouse scroll to zoom in and out on your 3D model. Alright, so in this particular and precise manner, I can meticulously move around within this digital environment, carefully positioning and aligning every single element and component properly and with great precision. Furthermore, in this specific section of our workflow, we are dedicated to thoroughly going through and meticulously inspecting all the various surfaces and intricate geometries that our sophisticated three-dimensional model encompasses and possesses, ensuring their integrity and accuracy, and then diligently checking each and every one of them for any potential issues or discrepancies. Naturally, the more surfaces we select, we'll have a more accurate result. But since this video is just an instructional video, I won't go into more detail and we'll move on to the body tool, because there are a lot of traces here that we need as well. We use the trace tool. So, I select this tool and I need to identify and traces. Here, I have a very clear trace. For example, I click once at the starting point of this trace. Then, I click a little further ahead to continue the trace. This segment is automatically picked up, and I continue to trace along the path. The algorithm we're using here is actually darkest point, which traces along the points that are completely dark in color. Because the traces themselves are usually darker in color compared to the surrounding points. This way, I can easily move along the model and trace it as far as the path continues. It's better to select points that are close together so the tool can follow the path more easily. Alright. After you've traced the entire path, you click this checkmark to close your trace. Now that you've identified the trace, you can use the picking tool to select it. You're right here. This is the trace you've identified. There's an extra part at the end of your selection. Just keep in mind that all these selections are added inside a folder called Measurements. These are the areas I identified using the Line tool, and the last trace is the one I identified using the Trace tool. Here's an important point. If we want all of these to be together, actually the purpose of identifying traces is to see the traces themselves, because identifying the areas is not always connected. So for this purpose, I need to make a very simple adjustment here. If you go into the Settings section here, there are a few options here, and you can check or uncheck the normal option. If I uncheck the Show Name option, or actually check it, the names of the identified surfaces will also be added, and here, for example, deep and its direction are added as labels on each surface, which is good. But it makes our work a bit messy, so, for this reason, we prefer not to check this option. If I uncheck the Show as Solid option, you'll notice that the color of the fitted surfaces will be displayed as a solid fill. But if I check this option, it will be shown as transparent, which is better because we can also see the background model. But the first option is Fit Plane. If you check this option, whenever you select a trace, it will automatically fit it to the surface, and instead of just showing you the outline of the trace, it will display it properly. Alright, here I'll go ahead and delete the trace I had selected. Now, I'll use the Trace tool and trace it like this. Now, as soon as I finish this measurement and check this option, the tool will automatically create a surface and fit it to my trace, which might not be very noticeable here, but in this section, this is the surface that the Trace tool has fitted onto the dependency. And you can see that by default, a certain control comes up and does this clipping. We have to go in every time and manually disable it. So, just like that, we can go ahead and trace the rest of our shapes as well. As an example, I'm only tracing a few of the shapes here. But if you're working on a real project, you should be much more careful and make sure to trace all the shapes you see as accurately as possible. Notice that right now, while tracing this shape, we see that in these areas, the tracing wasn't done correctly. What should we do to fix this? You can use this option here, and by the number of undo clicks you make, you can go back and correct it. That's all you need to do here. You can do the same thing for detecting edges using the Trace tool, so that you can identify the edges more easily. Now look, for tracking traces, this arm comes in and, as I mentioned, it follows the key points. So right now, it's tracking this trace. It follows the key points and connects them together. But if I wanted to follow the bright points, for example, the traces that you have on your own map are usually shown with a bright color, which is the filling bright in geological materials. So in this case, you need to have it follow the bright color. Well, you can very easily go to the Settings section in the algorithm and select the Lightness option. Here, we also have another option called Curvature. If you select this Curvature option, it allows us to easily highlight the edges with it, because it follows the areas where there is the most curvature. If I click on this section, it first needs to calculate that curvature. And then, based on that, we can highlight it. Depending on the size of your model, this might take some time. Now, let's continue in that order. Now, it easily follows that edge for you. If I click again, you'll see, it went ahead and, based on those edges you carefully selected, fit that surface as well. So, up to this particular point, It's enough for us to clearly see that after we've meticulously picked these surfaces, how we can actually analyze and interpret them effectively. As I previously mentioned, all the surfaces you've diligently selected are readily available in a dedicated folder within the software, right here, so you can easily export this folder and have the essential data conveniently at hand. In Cloud Compare, there's a very useful feature called StereoNet that lets you visually view the orientations of the surfaces you've picked and gain an overall sense of the orientation and distribution of discontinuities present in your rock sample. To accomplish this, you simply select the folder containing these measurements and then choose the StereoNet option here. If it's not readily available in your current software version, you can navigate to the Plugins tab, then proceed to Facets, and the very last option is Stereogram. With the default settings for main sectors and resolution, it will automatically display the StereoNet for you. Now it's much easier to clearly see, and in this manner, you can obtain a comprehensive overall view of the orientation and distribution of discontinuities within your sample. But if you don't wish to utilize this specific tool, you can export your measurements and then visualize them with any other preferred tool. To export, simply go to the Compass plugin, and here there's a convenient Save option. Whether you click here or in this particular section, you can export your file as a text file or a CSV file. Choose the desired destination and provide a suitable name, and then save your valuable data. I've saved the data in the Documents folder. If I navigate there, you'll observe two distinct CSV files, one for the lith data and one for the plane data. Actually, the specific data I am interested in is the plane file, which precisely contains the discontinuity surfaces. I'll proceed to open it. Here, there's a considerable amount of information regarding the surfaces it fit, their accuracy, and various other geometric details, but what truly matters to me is the strike, dip, and dip direction. So, I'll proceed to remove the surface name since I do not require it. The truly important columns are strike, dip, and dip direction. Now, I'll open the software Orient. I'll present a separate, dedicated video introducing Orient in more detail, but for now, I'll simply paste the data we have collected into Orient. You can clearly see the strike and dip here, and then, by carefully selecting the StereoNet option, you can view the data distribution on the StereoNet within the software. Now, I want to compare the StereoNets from Cloud Compare and Orient so you can clearly see whether your measurements are accurate or not. As you can observe, your measurements on both StereoNets show almost the exact same positions. The important point I wanted to particularly mention is that Cloud Compare utilizes the upper hemisphere for its StereoNet display, but in structural geology, we typically use the lower hemisphere. If we go into the settings in Orient and select the lower hemisphere, you'll clearly see that what we commonly use in engineering geology and rock mechanics is indeed the lower hemisphere, and this StereoNet is perfectly acceptable and much more familiar to us. But in Cloud Compare, what is shown is based on the upper hemisphere, so please keep this important detail in mind. Thank you for your kind attention.